Hello, everybody. I hope everyone's good, having a good lunch. Thank you for inviting me along to do this. So over the next 15 minutes or so, I'm going to be talking a little bit about the tool that I've written, which is called AreoBrowser. I'm going to start by looking at exactly what it is, what you can do inside of it, and a little demo as well. I'll then be talking about a couple of very specific tech challenges that I had when creating the new version of AreoBrowser. And then at the end, I'll talk a little bit about the future of it as well, that may touch on a bit of the AR stuff too. Now, before any of that, however, I want to just say hello, introduce myself a little bit. So my name is Marie. My background is not in science, planetary science, anything like that. It's actually in visual effects, more software side of things, really. And in the visual effects industry, I do efficiently. And in the visual effects industry, there were, broadly speaking, there was image processing problems, there were 3D data generation and manipulation problems as well, and there were data management problems too. And probably right now, a couple of you are nodding your head because, of course, the space industry has exactly the same problem set. So this is really good for me because obviously it means that I can come in and start writing a couple of little tools that hopefully increase accessibility of things, hopefully push data in a few interesting new ways, and also help people out along the way too. So let's start by looking at what exactly AreoBrowser is. So it is that thing you can see on screen. It is a 3D web app that you can all visit once the lunch is over at areobrowser.com. It uses two big web technologies, really. One is React for the front end, the actual web kind of structure. The second is Three.js, which at this point is pretty much the de facto way of doing kind of 3D visualization web experiences. It allows you to search and explore DTMs of Mars directly in your browser without a need to download any software, and it works on desktop and on mobile as well. Now, there's a couple of interesting things, obviously, in trying to make an app that works smoothly and stably and fluidly on desktop and mobile too, and I'll touch on that a little bit later on. But for now, I want to tell you how it came about. I started with an app, a Mac app, in fact, called Areo, which just proves that I'm terrible at naming things, into which you could drag and drop high-rise DTM files, pretty quickly see a 3D preview in front of you, and then export that out to a common industry format. So in my case, it would be JPEG. And this happened pretty quickly. This was pretty smooth in the end. So it was kind of cool. All of the data, the high-rise data available on the web. So I set myself a challenge to do it a month. A month later, I released version 1 of AreoBrowser, which is what you can see on the right-hand side there. And this version 1 I was super happy with, super proud with. It was a great proof of concept. It had 500 models in it, which was the entirety of the high-rise data set at the time. It was high-rise data only, though, which was one key thing I touch on later. There was some form of texture loading in here. You can't really see it that well because if you're familiar with high-rise DTMs, you'll know that the shaded altimetry texture that I'm loading is actually quite flat and quite gray, and maybe not the best choice for 3D visualization, but it did work, which was an exciting thing. The real downside to all of this was that the models were being pre-generated by Areo, the app I just showed you. So my pipeline at this point was this big Python kind of pipeline that would convert on the command line all of these high-rise IMG files to OBJ, upload those to AWS, and then when you selected something in that list on the left-hand side, you would download the OBJ, load it in Three.js, and then you could navigate around it. And this worked, and it was great. But the problem with that is that it's a lot of I/O, right? You're downloading a lot of information. I'm uploading a lot of information. There must be some way to do that a little bit more efficiently. So I went kind of back to the drawing board with all of this, kind of investigated a few more modern web technologies, and kind of thought about where I really want to push AreoBrowser over the next year or so. And a few months back, I released version 2, which hopefully immediately looks a little bit smoother and sleeker and nicer. But the key thing with this is that, first of all, there's now 1,952 models inside of here. So 4 times as many, because we're now introducing multiple data sources. So inside of here, I now have HRSC DTMs as well as high-rise DTMs too. I'm also chatting to a few other people about maybe putting some of their generated DTM data into AreoBrowser as well. And it's a bit of a spoiler for my final slide, but if you are interested in getting any 3D stuff visible in AreoBrowser, please do get in contact and let me know. So alongside these multiple data sources, there are now support for full color texture loading. So in this example, you can see on screen, we're loading a full kind of grayscale image here, draped over the high-rise DTM. Some of those HRSC DTMs also have full color imagery laid over them too, and I'll show you that in a second. I'm also generating normal maps, which I'll talk a bit more at the end about, but basically it's a way of increasing the perceived quality of the mesh. Finally, the most important thing for this version and kind of going forwards is that the models are now generated in the browser. So it's no more of this kind of pre-canned, making a model, uploading it, downloading it, viewing it. Basically, you choose in this left-hand list what you want to see. The browser is then doing the hard work of converting a custom encoded format I've created into a 3D mesh on the fly, directly in the browser when you need it. And this is super exciting for going forwards. So let's have a quick demo. I'm just going to come out of Keynote quickly, hop over into Safari. So this is AreoBrowser.com. This is the first screen you'll see when you go there. There are some instructions at the top if you want to get really good at the keyboard shortcuts to navigate around. There is contact, of course, if you do want to get in touch and kind of let me know that you've got data you want to put up in here, or if you find a bug, either's good, just let me know. And then there's the credits of all of the data that is available within the application too. Now, on all of these pages, you have this Start Exploring button at the bottom. You just click that and take you straight into the 3D view. So immediately you can see it's loaded the first DTM that's available. You can select any of the ones you want from this left-hand list. As I said, there's 1,952 items in here. We're nearly at 2,000. I'm going to celebrate massively when we get to the 2,000 mark, but you can lose a lot of time basically just scrolling this left-hand list and clicking something random. It very rarely comes up with something bad. The data sets are just amazing to work with, and it's such a beautiful thing to increase the accessibility of and get in front of more people. Now, of course, you can search up here. You can search based upon the name or the data ID of the images involved as well. You can filter based upon the instruments. You can also sort by things like the date that it was added to the site, the elevation difference of the model, that's between the valid minimum and the valid maximum of the DTM, and the ID as well. But let's go in here and just search for Gale Crater. So you can see there are 16 items immediately that become available for Gale Crater. I can click one of these and it immediately loads. I can click another one and it immediately loads. And just to be clear, these aren't cached. These are coming in live, downloading from the web. But the key thing here with that custom format I mentioned a minute ago is that it allows me to have this really quick loading process now. There's no like spinner while you wait for something to download. You just click and immediately see something inside the 3D environment. So let's just find something here that we can settle on. Maybe this one, that's like pretty cool. So over on the right-hand side of the screen, you can see we have this settings cog. Inside of here is where you choose all your qualities. So let's just close this up data panel for a second. So at the top of this first section, the material section, we have this image quality slider. So I can choose from low, normal, high, or maximum quality. At the moment, it's set to normal, so let's just zoom in and take a look at this. If I set this to low, it's for really low bandwidth kind of connections. It will automatically choose low if it's really kind of slow data transfers are going on. But you can obviously go all the way up to max and pull in that maximum data available for a particular DTM. You can also toggle the color images. You can do that with the C key on your keyboard as well. If you just want to see the mesh, and some of these are just really quite beautiful. And if you just want to toggle that on and off, you can see the difference, that color texture is making. And finally, we have this normal map that I talked about earlier, and I'll touch on more about that in a second. But basically, you can see if I turn this off, the quality of the mesh appears to decrease. The poly count of the mesh actually isn't changing. It's just the normal map is increasing the perceived quality of the mesh that has been generated. The next section gives us this model quality. Now you could push this up to max if you want. Because I'm screen capturing and recording and all that kind of stuff, I'm not going to. The maximum level of quality we allow in here at the moment is 12 million polygons, which for those of you who do kind of 3D processing know is quite a lot to have inside a browser. So use max sparingly, but low, normal, and high is pretty on every machine I've thrown at it. So we also have a vertical exaggeration option. So if you want to look at kind of low-lying sections of terrain in here, you can crank up the vertical exaggeration to make that a little bit more easy to see. That's also the 1 to 9 keys across the top of your keyboard. There's an altimetry section for viewing a gradient with added contours that you can change the spacing of if you're interested in this kind of visualization. And also you can turn the grid on and off as well, which is, you know, just necessary in this case. I'm making a few things at the moment to add downloading of meshes directly from the browser at varying proxy resolutions, as well as better image downloading too. So that's coming soon. Just before I finish up the demo, I want to quickly take a look at the HRSC data. So let's actually sort this by elevation. Click on this. And again, if I toggle on that color map, this is just stuff that you can really kind of easily lose yourself in for quite a long time. It's just an amazing data in both datasets. Importantly, just before I forget, because it was hidden behind the zoom thing, at the bottom of the screen, you have the lat long elevation and the grid scale as well. And this updates to see the point under the cursor as well. And that takes that vertical exaggeration into account. So you're not going to see bizarre values if you increase the vertical exaggeration of mesh. So I think that's cool for the demo. I'm going to head back over into Keynote and continue where we left off. So there's obviously a couple of technical challenges in bringing this kind of DTM data to the web. But fundamentally, taking a step back, when you create an app like this, there's obviously that question of, is it kind of more for outreach or is it more for science? And I tend to want to lean more to the second one, because personally as a developer, there's probably more interesting technical challenges in that one. But kind of if you go even broader on this, it's a question of speed versus accuracy and accessibility, like how quickly can you find the data that you're after, versus complexity, how deep can you go into the data should you choose to do so. Now, I have a huge range of opinions on all of this, which I'm sure most of us here do, but we don't have time to go through all of them, so I'm just going to concentrate on the speed versus accuracy thing and talk about a couple of the challenges surrounding speed and accuracy in AreoBrowser 2. So I mentioned earlier that I created a custom elevation encoding, and I want to walk you through how I did that. So let's take a random kind of high-rise DTM. So this example here with the preview color altimetry image on the left-hand side. The full IMG file for this DTM is 424 megabytes, which is clearly way more than you would ever casually download in a web viewing experience. So we really need to get that file size down to increase the speed that you can load these files, but we want to try and maintain as much of that accuracy as we can when we do so. One of the good things with this is that the data in the raw image is 32-bit, which again, we don't need in a web environment. Web is almost entirely 8-bit in format, and it will happily handle 8-bit images, but 32-bit, it takes a lot of custom loading, custom tech to do that kind of thing. So it would be interesting to see how close we can get in terms of accuracy to that original raw format. And it turns out, actually you get quite close. So if we take the 8-bit RGB format that pretty much all web images come in, that basically means that every pixel in the image has a red component, a green component, and a blue component. And each one of those components has 256 possible values between 0 and 255. Now, if you do the maths on this, 256 times 256 times 256, you can realize that there are 16.5 million-ish possible values. So there's 16.5 million possible ways to encode an elevation into a single pixel on an image. And that's what I did. I basically took a binary format, that high-rise IMG file and the HRSC IMG file, and I mapped its values into that known range that we now have. So to walk you through that, each DTM has a valid minimum and valid maximum point. That's the bit of data that we're interested in, essentially. So we can find those values, the minimum and the maximum. We can map the minimum to 0, the maximum to that 16 and roughly 0.5 million, and then we have our new range data. The second step is to then take that new range and convert it into 3 separate 0 to 255 RGB values. And if you display those RGB values in an image at that point, it looks something like this, which is clearly massively chaotic and not really designed for human eyes, but I'm getting weirdly good at reading them actually. But the key thing with this is that it encodes a lot of the accuracy of that image on the left, but at a much reduced file size. So let's take a quick look at the stats. I'm just going to take a quick drink of water. So on this image, there is a valid min and a valid max, and the elevation delta, the change between those two, in this case was about 1 kilometer. So what we know we need to do for this specific DTM is encode that kilometer of elevation change into the 16.5 million possible slices of elevation that we have per pixel due to that 8-bit RGB format. So we can do the maths on that. We can take that roughly 1 kilometer and divide it by the 16.5 million pixels, 16.5 million possible values, and we get this resolution. Every step I go up in pixel is equivalent to 0.06 millimeters of real world elevation. So the resolution I'm getting in this final image is sub-millimeter. It's incredibly accurate, which is pretty awesome. So just to show this a little bit further, what this now means is that now we've got this really, really accurate data. It's completely decoupled from the resolution of the image. Which means that I can now downscale that original DTM to something much, much, much smaller, but still see something pretty accurate in the web browser. So in AreoBrowser 2, the smallest image that we download is this one. It's 512 proxy. That's a 14 by 27 pixel image. It is incredibly small, but incredibly accurate. It comes in about 1 kilobyte, just over 1 kilobyte really, and it's the first thing you load. If you catch it quick enough, you'll occasionally see this quality of model in AreoBrowser. The next thing we download, once that's in and loaded and displayed on screen, is the next version up. So we basically, again, double the width, double the height to increase that resolution, keep increasing until we get to the highest proxy level that we support for this DTM, which is proxy 16. Now you can see in here we've got a much bigger image, which is obviously a greater file size, but that file size is way lower than the equivalent object, the 3D mesh object would be if I was asking you to download that. Doing this directly in the browser generated from this image is way quicker. It involves a lot of modern web technologies, makes the whole experience much nicer, and the file size download is much smaller as well. Converting this to polygons at this point, we basically take every pixel in one of these generated images, we turn it into a vertex in a mesh, we scale that mesh up to the known size of the DTM, we end up with a resolution for the mesh, which is actually really pretty decent for a in-browser 3D object. So just to show you this left to right, on the left there we have a proxy 64 version of the mesh, we have a proxy 32 in the middle, and a proxy 16 on the right hand side. Now obviously there's an increase in file size as you go from left to right, but you can see the elevations aren't changing, it's just the detail that's increasing inside of there. So even from the lowest proxy levels, those smallest images, the elevation is pretty accurate. I just wanted to include this as well because I sent out this tweet a couple of weeks ago. I can't remember exactly when it was, but it was the first time that I'd actually done this maths in my head. So the greatest elevation difference of a single model in AreoBrowser is currently roughly 24 kilometers, which if we run it through the exact same process, gives us that elevation kind of level, resolution level of 1.43 millimeters, and high-res accuracy is about 25 centimeters, so we're well within the limits of what we might want to do here. So that's one way of approaching this speed versus accuracy problem. The real issue with this, which I'm sure some of you have picked up on at this point, is that I'm not using the full resolution of that original binary IMG file, right? We're downsizing it, we're using a proxy version instead. So we're never really going to load the full version in the browser. It's just not the place to do it. I'm a firm believer in tools doing one thing well. And if you want like 32-bit data that's full resolution, you're probably not going to be doing it in a web browser at that point. You're going to be doing it in a dedicated tool. But we can get somewhat close by utilizing something called a normal map. And normal mapping is a technique that's primarily used in the games industry to increase the perceived detail of a mesh without actually increasing its resolution. Because as you add more polygons, obviously load times slow down, navigation slows down as well. Such a bad thing. You want to avoid it when you can. So you can introduce these normal maps. Now, to distinguish them quickly, a color map, the texture that you might be used to in a 3D environment, encodes obviously the color of the surface at a particular point on screen. A normal map, which is this purple object here, actually encodes the direction of the surface at that point on the screen. So it's a vector representation rather than a color representation. The key thing with this is that if that normal map resolution is bigger than the source resolution I'm using for my models, then the perceived resolution will always be higher. Now, to show that a little bit more clearly, I've got a couple of examples here. Now, this is the lowest possible mesh resolution that you've got for the current loaded DTM file. You can see that with the normal map turned off, it's decent. The elevations are accurate. But with it turned on, you get that perceived increase in detail. And it's really the lighting in the environment that's doing this work for us, coupled with that normal map. But it's like an order of magnitude of perceived resolution difference. And this is generated from that full resolution DTM model. So everything you see here is accurate in terms of placement and perceived depth. Here's another quick example on another DTM. This one is probably more drastic. You can see, the perceived details in there are just, there's a huge difference with that toggle on and off. And that really comes into play when you're navigating around and you can see the light differences on the model. So finally, I just want to quickly wrap up with what's next for AreoBrowser. So the first thing is hopefully something you might be able to help me with, and that is more sources of information. Like I said, I'm chatting to a few people right now, but if you know of 3D data that might be good to get into AreoBrowser, if you are creating 3D data that might be good to get into the AreoBrowser environment, please do get in touch and let me know. I would love to get as much in here as possible. The second thing is introducing the concept of viewing multiple DTMs at once. So that resolution trick with the proxying that I showed you a second ago, right now that's controlled in the settings panel. But behind the scenes, there's a toggle that I can just switch on, and it makes it controlled by the altitude of your camera. Now, what that means is that as you are really far away from the model, its resolution will be quite low. And as you zoom in closer and closer and closer, the resolution will increase and increase as you, zoom into the bit of the object that you're more interested in. The cool thing with that means that if you zoom out far enough, you might see other DTMs scattered around the current one that you're viewing, be able to click that and go over to that DTM instead. That then leads on to the next logical step, which is the full planet view, which I've been working on for a little bit. It's very early days, but it's very exciting. Essentially, it would be a molar representation, very far out. And then as you zoom in, you would be able to see the different DTMs available in AreoBrowser scattered around the planet. And they would initially start at low resolution, then get higher and higher resolution as you zoom in. And finally, of course, there is AR. I'm working on an iOS version of this for exactly the same reasons that Andrew mentioned at the moment, which allows us to do cool kind of multi-user collaborative sessions with this kind of data across iOS devices, which I think is really pretty exciting. So that's it. Thank you so much for listening. I hope you do play with the site. Give it a go. Let me know how you get on. Again, if you've got suggestions, if you've got bugs, let me know, and we can chat about either getting them implemented or getting them fixed. But I'm always open to chat about this stuff.